In this video I'm going to demonstrate how to solve a set of nonlinear equations in Matlab using fsolve. And to demonstrate I will use these equations, so the equations for an evaporator. So let's assume in this case that the unknowns are the flows L, V and S, so the liquid flow out, the vapor flow out and the steam flow. And let's also assume that the area is unknown. This is the same as example I7 in my compendium. Okay, so let's dig into it. The standard way to solve this kind of equations are to rewrite them in residual form. What that means is that we rewrite, so instead of F equals L plus V, like this, as we had our equation, let's rewrite it so that we have everything on the same side, so L plus V minus F. That should be 0, right? If F, L and V satisfies this first line here, then this should be 0. So we need to put that result into something. So let's put it into a vector, the first position of a vector. So there's our first mass balance. Our second mass balance, we do the same thing. We move around so we have everything on one side. So L times XL minus F times XF. Then we have our first energy balance. So V times HV plus L times HL, so H being the enthalpies, right? Minus F times HF. That's on one side of our equation. In our equation on the other side we have S times HS minus HK. So let's move that to the same side. HS minus HK, like that. And our fourth equation is also an energy balance. So we have the energy balance over our heat exchanger. So K times area times Ts minus RT. And then on the other side of the equation we have S times HS minus HK. So now we have 4 equations here, which all should be 0 if we guess our L, V, S and area correctly. Let's put this into a function. I will call my function evaporator. We have to call it with an argument, our guessing values. Let's call that x. And let's put an n down here. Okay, this has to return something, so we know where our guess is good. So let's call it y equals evaporator of x. So what happens now if we call this evaporator function is that it calculates these y values, and if L, V and F are correct, then all these should be 0. But we have to tell this function what L is, right? So we translate x to variable names that are more easily understood. And it doesn't matter in which order we put these. So let's say that we have L as our first position in X, and then we have V, and then we have S, and at last we have the area. So that's position 2, 3 and 4. So now we have L, V and F, but what about the other guys? We have XL and XF here. Well, for this to be a solvable system, we have to know these. So how to deal with this? Well, why not put in a new vector here, known, where we put everything that we know. So we translate the known parameters to variable names that are more easily understood. So let's say, for example, that XL is the first position in known. and XF is the second. Perhaps we need more. We will see. Okay, what do we have more? We have HV must be equal something. We have HL must equal something. HS, which is also a vapor, has to equal something. HK has to equal something. So let's see, we have HV, HL, HF has to equal something as well. HS, HK, we have said TS and T. We have to know TS and T somehow. So let's say that T is our third known. What about TS? Well, you could of course say that TS is our fourth known, but let's instead use the pressure of the steam as our fourth known. That means that we have to calculate TS somehow from PS. So TS should be a function of PS somehow. I will just paste that in here. So our TS equals this thing. This is the Antoine's equation. And to calculate HS from that, there is a nice correlation for that as well, and I will copy that in as well. So we have a temperature polynomial here that gives us the enthalpy. So we have now HS. For HV, we do the same thing, the same equation, but another temperature, so not TS here, but rather T. What about the enthalpy for the liquid streams? Well, we need to have a CP for water. Let's say that that's 4.2 kilojoule per kilogram and degree Kelvin or Celsius. And we need a CP for the solids as well. Let's say that that's the same for simplicity. And for the condensate, that's pure water, right? So that's only CPV, and let's assume that our CP value, the heat capacity, is the integral median value. So we can just multiply CPV with the temperature of the steam. For the feed and the liquid coming out, it's slightly more complicated, right? Because this is not only water, it's water and something else. So the CP value for water should only be multiplied with the water part. So that's 1 minus XL. And the other part should be multiplied with the other CP value for solids. Something like that. And not TS there, this should be TF. And similarly for HL, we should multiply here with TL, and then we have, sorry, that should be XF, right? It's easy to do wrong here. So XF there and XL there. So this should be right, I think. So let's try to call this and see if we did everything right. So we call evaporator. And I have to have guess values here. Let's just put in 1s for the flows and 100 for the area. So 1, 1, 1 and the area. And then I have to add the knowns here. Let's take the knowns that we have in task I7. In that task, XL equals 0.25. XF equals 0.05. The temperature of the feed is 80 degrees and the pressure of the steam is 2 bars, so that's the same as 200 kilopascal. So let's see what happens. unknown function or variable evaporator. Why is that? Well, it's because I called my function evaporator and the file is called evaporator demo. My mistake. So let's call this evaporator demo and save that. And let's go back and say evaporator demo. Cannot find an exact case sensitive match for evaporator demo. Do you see my mistake? There's a big letter E there. So many ways to do it wrong. So let's do it like that. And did you mean evaporator demo? Yes, I did. Okay. Cannot find an exact case-sensitive match for TF. So you see, there are so many ways to go wrong here. You can click on this line 24 there, and then you come directly in here. And you see there is a TF there. And what did I do? I said up here, I said T equals known, but it's not the temperature in this task of what comes out that is known, it's the temperature of the feed that's known, so it should be TF there. Oh, sorry, small f there, because I have small f there. And now I think it should work. It still doesn't. Undefined function or variable t. Let's go back and look at the exercise. The pressure in the boiler is 1 bar. 1 bar, so 100 kilopascal. That means that the temperature here is actually also known. So T is also equal to known, so that should be a fifth. And that's the temperature. What we could do, why not take the pressure? Pressure is known, and then we can say, copy that thing there and say T equals, and there should be a P there instead. So now we put in the pressure as a known, pressure in the condenser, and then we can calculate the temperature of the liquid out. And now we go out here, and then we have to add a second known. It was 1 bar, so 100 kilopascal. Error in undefined function or variable TL. You see, there are so many ways to do mistakes here. I introduced a T, but I called the temperature down here TL. And there's another thing here. You see? The T there, that should be the TL, right? So many ways to do mistakes. I still have it somewhere. Yeah, there, TL. So when you get these error messages, always take the first one. And then click on that line and see where it, and read the line there, undefined function or variable T. It says pretty much what the problem is. And let's try to run it again. Undefined function or variable F. Yeah. That should also be known, right? So F, we need to add another known, that we have 1 ton per hour. So that's also a known. 1 ton per hour, that's 1 10 to the power 3 divided by 3,600 kilograms per second. And then HL is unknown. Didn't I calculate that one? No, because I did wrong there. See, I copied that line and I forgot. There's so many ways to do mistakes. Undefined function or variable K. I forgot K. That must also be a known. K equals known number 7. The K value here should be 1.6 kilowatt per square meter in Kelvin. 1.6. Error indices must be positive integers or logical you see what I did there? I forgot the multiply sign. Multiply character. Like that. Okay, so with these guesses, I got an answer here, and those answers, those are my residuals. Okay, so I haven't solved anything yet, right? So what to do now? Let's write a function that calls this function through the fsolve command, or in Matlab. So let's put this into something new like this. And now we can call this one Evaporator down here. And we have Evaporator demo up there. And this main routine up here should be the one calling the thing down here. So we can try to do that. Just copy this thing in here. And now we should call it Evaporator, since I changed the name down there. I changed it so that this the main function here has the same name as the file. That's the way to make Matlab find things. So if I now write Evaporator demo with no arguments, then I should get the same thing, right? Because then Matlab runs this thing, and then we come to this line, and then it immediately goes into this one. Okay, let's put these things in here into a variable called known. We write known there. Known equals this thing here. And perhaps we need a comment there. Order of known, that was XL. And that we can see down here, right? XL, XF, TF, PS, P, F, and K. And these things here, those are our guesses. Let's just copy these ones for now. Now, we need to call this with fsolve. So fsolve should do something with this thing here. And the way to do this now is to say, this is the unknown bit, right? Let's call that unknown. And how do fsolve know what to do? Well, we should tell it that the variable to iterate on is the unknown. So this argument here. That argument, that's the thing that fsolve should iterate on, and we need to give it a start value for the guess, like that. So let's see if this works. I should now be able to call it Evaporator demo. Undefined function or variable unknown. So why is that? Well, that's a bit tricky to figure out. But as it happens, I've actually used the wrong syntax. Let's write help fsolve. If you see here, it should be a parenthesis there. Solve at, and then parenthesis, and then the thing in there. Okay, let's try that. Let's put the parenthesis in there. And let's go out here and try to run it. Invalid expression when calling a function or indexing a variable. Let's go in there. I think it should be like that instead. Not a comma there. If we see, look at this one again, the help. Here you see if I, let's see, there, at X, and then there is no comma there. So this should work. And now I got answers. So the answer is 16 square meters. and the order, which order did we have? We had L, V, S, and A. Let's put the code in here and say result equals fsolve, and then, because then I don't have to redo the calculation by hand. SV tot equals the result. Okay, let's use small characters there, so it's so easy to do the wrong thing here. Res3 is our S value, and res2 is our V value, and since we only have one evaporator, we only have one vapor flux out, so this should be our S V dot. Let's take away the semicolon so it actually prints out. So S divided by V dot is 1.07, which is fairly good, right? We can actually try to do something else here now. We had 80 degrees here as our TF. Let's change that to 20 and see what happens. Let's run it like this. Since we don't have any arguments here, we can actually press run here, and then we'll run the main function. And now S divided by V dot becomes 1.2. And why is that? Well, it becomes that because now some of the heat is used up as heating up the feed instead of just using it to evaporate the feed. And we can check here. Let's try it 120, see what happens. Then we got less than 1. This means that when the feed comes in, some of the feed flashes and turns immediately into vapor. So that's a way to use Matlab to solve nonlinear equations.